to the latest episode of the Galileo Interviews. My guest today is Professor Kaxiras, whom I had the pleasure of visiting at Harvard University. You can find lots of information about him in the description, but let's get straight into the discussion. Enjoy. So, thank you for joining me. I appreciate your time.
Okay, it's a pleasure.
So, when we're young and we're first taught about materials in school, the first thing we're often taught is the solid, liquid, gas model of everything. In a more general sense than that, what is a state of matter? And in your, I'm sure, completely unbiased opinion, what's the most interesting state of matter?
Yes, well, as you said, matter can be in these three basic forms, solids, liquids, or gases. And all three are different ways of arranging the atoms in space. And for me, the most interesting one is the solid phase. This is most of the materials that we see around us and we use in everyday applications. And solids are really fascinating because they themselves have a huge variety of structures, of properties, and that's what makes them so useful for humanity. And figuring out exactly how the atoms are arranged to make up a solid is a very interesting problem. Most commonly, they are arranged in very regular patterns, the crystals. There's many different types of crystals, and the specific crystals and their composition, the structure of the crystal and the composition in terms of different elements that participate in its formation is what gives the materials this huge range of interesting properties. Some of them are transparent, some of them are not, some of them are insulators, some of them are very good electrical conductors, some are magnets, some are not. Some are very tough. You cannot bend them. They break very easily, a property that we call brittleness. Some are very ductile. You can bend them and they don't break under very large stresses. So it's a huge variety of properties, and this is exactly what we need to have all the applications that make our life easier and more comfortable and so on.
So when you're trying to model at the, atomic scale,
Yes.
I imagine there are quite a few challenges associated with that. How do you go about doing it? What are the challenges? How do you simplify the problem?
Yes, absolutely. So if you really want to understand what happens and how different solids and materials acquire their properties from the atomic structure and composition, you need to understand what the atoms are doing. So how each one behaves when it has a certain number of neighbors and so on. And how atoms form bonds between them, chemical bonds that hold the whole structure together. So in order to really understand this at the most fundamental level, you need to invoke the most basic laws of physics, the laws of quantum mechanics. So it's quantum mechanical, the quantum mechanical nature of electrons and ions that determines exactly how these atoms behave, which then translates into the properties of the entire solid and the material and so on. So in understanding this at such basic fundamental level is a big challenge. Because quantum mechanics itself is a very interesting, kind of weird theory. We still don't quite understand intuitively how quantum mechanics works. We know exactly the laws. We can write down the mathematical expressions that capture these laws of nature, but it's not easy to intuitively grasp what is implied by these laws. And it's not easy to solve the mathematical equations that represent the quantum mechanical description of matter at this fundamental level. So some great physicist once said that we don't really understand quantum mechanics, we just get used to it. So we know the basic rules, we know how nature is supposed to work, and we get used to operating with these laws, even though it's hard to intuitively grasp them, because at a basic level, these laws say that electrons and ions behave in a very strange way, very far from what we are used to from the macroscopic level which we see things, and this is what makes the laws of quantum mechanics hard to understand intuitively. For example, there is this idea that everything is based on probabilities. It's a probabilistic theory at some level. And that's not easy to accept. Even Einstein used to say, God doesn't play with dice, so meaning that he didn't really believe the laws of quantum mechanics, even though in the last 100 years or so, since the development of the quantum mechanical theory in the 1920s, all the experiments that have been made to test that theory have proven it correct. There's no single experiment that contradicts the prediction of quantum mechanics. So it's an incredibly successful theory.
Right, yes.
And that's the theory you have to apply to understand at the fundamental level how solids behave based on their atomic composition.
Okay. So what's an example that comes to mind to demonstrate that when you're dealing with materials?
Yeah.
What's a good example of something that's the result of quantum mechanics that is really weird and defies all expectations?
Yeah. Well, there's all sorts of strange things happening. For example, if you under normal conditions, electrons, which are charged particles, very tiny charged particles, part of the atomic structure, move through a solid, and as they move through the solid, that's what carries electrical current, and they keep bumping around on ions among themselves and so on. If you cool the system enough, at relatively low temperatures, the electrons find a way of arranging themselves all together, and by so doing, they can move through the solid without experiencing any resistance. So this is a state that we call superconductivity, the superconducting state. And it can only be understood based on the laws of quantum mechanics. There's no classical analog of this. There's no way to say that a bunch of charged particles all of a sudden decide to move in such a coherent way, such a coordinated, correlated way that they avoid any kind of bumping around with other obstacles like other atoms in their path or other electrons and so on. So this is really very bizarre if you think about it. And we're talking about a huge number of electrons that participate in this coherent collective motion of order 10 to the 23rd, which is a really astronomically large number. But that's how many electrons are in a typical solid. And all of a sudden, if you cool the system enough, they decide to all adopt this very unique state.
What actually happens there at a sort of high level, without getting too technical,
so
so
this is a really fascinating topic. It was this superconductivity was discovered in 1911 by Kamerlingh Onnes, and in the lab. It was observed in the lab that at some point, the electrical resistivity just completely vanishes, goes to zero. That's the superconducting state. And it was some aspects of it were explained theoretically in the 1950s, but there are other aspects of it that are still not quite explained by theory. You don't quite know how it works. So basically what happens is an electron, because it's a charged particle, tries to avoid all other electrons that have the same charge, all of them negatively charged. But when the system is cooled down to below a certain temperature, then there's enough motion of the atoms, enough coherent motion of the atoms, that the electrons can take advantage of it. So as they move around through the motion of the atoms around it, acquire an attractive interaction with other electrons, which itself is very strange. So all of a sudden, particles that normally repel each other because the atoms have stopped fluctuating very much, they can take advantage of their environment and pair up. So one electron finds another electron. Basically, they're moving in opposite directions, and they can sense each other at a distance and pair up. And once they are paired up, it's much easier for them to all condense in this state that I was describing earlier. So these little pairs of electrons start behaving in a different way, fundamentally different way than individual electrons would behave. And again, that's something that can only be described within the framework of quantum mechanics. That's a purely quantum mechanical phenomenon. So electrons are referred to as fermions, which means that two of them cannot be in the same state. But if they pair up, then this composite particle, which is made up of two electrons, all of a sudden has very different properties. It's called a boson. And bosons can condense in the same state, can all exist in the same state.
Oh, that's crazy.
That's crazy, right?
It becomes, two fermions can become a boson.
Exactly, exactly. That's kind of crazy. Well, that's what quantum mechanics predicts, and we observe in nature. And that's how weird things are at this level.
Yeah.
And understanding them is a big challenge. But then, if we develop this level of understanding, then we can do all sorts of really amazing things, like in the superconducting state, the material that is superconducting expels magnetic fields. So if you put it on top of a magnet, it tries to expel the magnetic field, and it levitates. So it's just sitting on top of the magnet without ever touching it, and that's a really wonderful thing. I'm sure you have seen pictures of this,
very cool videos.
Yes,
and that's going around tracks.
Right, exactly. It could be used to have levitating magnetic trains or something like that. So, so there's all sorts of really interesting phenomena that once we understand them and are able to control them, they could lead to really wonderful applications.
Okay. So in the quest to control them, probably time to talk about Twistronics.
Oh.
So it sounds like a contemporary dance sort of name, but from the sounds of it, it's something much cooler.
Yes.
Could you give a sort of brief technical overview of Twistronics and what is its importance to material science and the future of it?
Yes, absolutely. This is actually probably my favorite topic, because we, meaning my research group, invented this term, Twistronics. And
it's a great name, by the way.
Thank you. Yeah, it caught on, which is great, very nice. And the idea is that you can work with materials that are essentially two-dimensional. That is, all the atoms in this material, very special material, are on a single atomic plane, a single plane. Actually, this originally was thought that this may not be possible based on some abstract theoretical arguments, but it turns out that it is possible, because the atoms on that single plane can have very strong chemical bonds holding them together on the plane. Then once you can do this, you can imagine putting one plane of atoms on top of another plane, and now the two planes are more or less floating on top of each other. They're not quite glued together as they would be in a normal material. So these are called layered materials, because it's possible to separate the layers and think of them as individual layers interacting very weakly. It's as if they're almost very gently touching one on top of the other.
Okay.
And there's a preferred way of stacking these layers. Preferred meaning the atoms have the lowest energy, the most preferred configuration. And if you let the system relax, it adopts this configuration. But you can also introduce a twist relative to this preferred stacking. And once you introduce this twist, then all of a sudden you get a pattern in the twisted system, which is very different than the original pattern of the atoms bonded on the plane. I actually have a little model to illustrate this. So here's my model. So these are the two layers. This is actually representing graphene. So all the little circles here represent carbon atoms, and there are two planes of carbon atoms sort of aligned on top of each other. And then you can introduce a slight twist relative to the perfect alignment of the two layers.
Right.
And if they are slightly twisted by a small degree, then if you go far away from the point of alignment, you see again matching regions, and that's called a moire pattern. But the regions where the atoms nearly match, the perfect match is destroyed by the twist locally, but again, very far away, they start matching again. So the scale, the range of distances over which they start matching again is called the moire length scale. So this now introduces a very different pattern than the atomic structure, which is defined by the bonds, the chemical bonds between atoms. And this much larger length scale produces a behavior in the electrons in the system very different than the original material. So for example, graphene is a metal, but a very poor metal. It's electrons can move very fast in these planes, but there's very few of them. So it's good in the sense that the electrons can move very fast. They're very mobile, but it's a poor metal in the sense that there's very few available electrons to do that.
Okay.
Nevertheless, it's a poor metal in that sense. And there's nothing other special about it. Now, when you have two layers of graphene with a small twist, then if you cool this system down to quite low temperatures, a few degrees above absolute zero, then it becomes superconducting. And this is something very surprising because materials made of carbon normally are not good metals, and therefore it was not expected that there will be good superconductors. So this was a big surprise, a huge thing when this was discovered. And we introduced the term Twistronics to describe that this little twist can produce these very interesting properties, and if you control the twist and also the number of layers that you have and the arrangement in space, then you can play these very interesting games and get carbon atoms, a material made exclusively of carbon atoms, to behave in extraordinary ways. Okay. So that's the idea behind Twistronics. Because under normal circumstances, the graphene layers of this material made of carbon atoms basically create graphite. Many of these layers create graphite, which is your what we call lead pencil. That's what's in your lead pencil, and that's why you can sharpen it, and that's why you can write with it, because as you write, lots of these layers are stuck on the paper, and that's what you see as the trace of the pencil. So that's normal graphene. But if you normal graphite, which is composed of many layers of these carbon atoms. But if you isolate a single layer and then by a very elaborate way put it on top of another one with a little twist, all of a sudden you have one of the most interesting types of solids, a superconductor.
So breaking down what's interesting about the structure, firstly, what's special about each of the sheets being two-dimensional? I'm taking it that's part of it in terms of the
absolutely structure. So as I mentioned earlier, people actually thought that it would not be possible to have atoms stable on a single plane, because the fluctuations getting away from this planar arrangement would destroy the stability of the structure. That's what theoretical arguments were suggesting. However, these theoretical arguments did not take into consideration the very strong bonds, directional bonds, as you can see here, though those are really representative of the types of bonds that you have, can hold the atoms on a plane. There's small ripples, but that doesn't destroy the planarity of the structure. When this was discovered, when a single plane of carbon atoms was isolated, that was a big surprise in itself. So that happened in around 2005.
By graphene.
Exactly, by two scientists at the University of Manchester, and they were awarded the Nobel Prize for this discovery, which was wonderful. This really produced a revolution in solid-state physics, because all of a sudden we had these systems of purely two-dimensional, all the atoms lying on a single plane, and their behavior was quite different than normal solids, which are three-dimensional crystals extending in all three spatial dimensions. It was not easy to do this, but the interesting properties of this crystal produce a tremendous amount of excitement in the scientific community. There was a lot of work done to understand this system, predict its properties, and then use it in different interesting ways. You can imagine that this could also make the ultimate layer as a membrane. So very few other atoms can get through this membrane, because even though you see these big hexagonal rings here, those are very, very small on the atomic scale, and basically nothing can pass through this, except if you intentionally create a few holes larger than the hexagons that you see. And those few holes can be intentionally created, and they only allow very preferentially a few types of atoms or molecules to pass through. So this is essentially the ultimate membrane which you can use to separate different substances.
Semi-permeable.
Exactly. Yeah.
Right.
Yeah.
That's interesting. So breaking down then the rest of the physics of what happens differently on a two-dimensional plane.
Yes.
What else is there to it? How come having the two-dimensional plane can then be used to create the effect seen with Twistronics? What's the next step?
Yeah. Well, if you have the atoms confined on a plane, then the electrons associated with the atoms are also confined in the same plane.
Right.
This was actually a goal of solid-state physicists for many, many years, but they were trying to accomplish this with conventional three-dimensional materials. So they were creating interfaces between three-dimensional materials. Imagine half of a material on this side and the other half of a three-dimensional material on the other side. And right at the interface, it was possible to capture electrons that lived only at that interface. But it was really, really hard to create interfaces that were very pure and very flat.
Right.
So crystals at the atomic scale are not very flat. No, there's lots of bumps and mountains and valleys and so on. So it was really, really difficult to do this. And for many years they tried to do that, and they achieved high quality flat interfaces. And then when you put this system under a magnetic field, electrons start behaving in other interesting ways. Because, for example, if you pass a current through this single layer of electrons, the electron and put the whole system in a magnetic field, the electrons have to execute orbits. So these are called Landau levels and Landau orbits. Under certain circumstances, the current that you observe is quantized, so it only has very specific values, again according to or the resistance has very specific values according to the laws of quantum mechanics. Moreover, if you arrange...
That's amazing that such a macro property is quantized.
Exactly.
Usually you'd see that with,
Exactly. So even though you have a huge number of electrons, because you confine them on a plane and you apply an external electric field, you force them to execute these orbits. The orbits themselves are quantized. They can't be any size you want. They are what the combination of electric and magnetic fields determine. And once the electrons form these orbits, then they have to, again, obeying the laws of quantum mechanics, behave in a certain way. And that's why the resistance of this two-dimensional electron gas, as it's called now, is different than under normal circumstances. It's quantized. Moreover, again, by choosing the conditions in just the right way, you can create situations where many electrons move together, form these more interesting correlated states. So effectively, the particles that are doing the conduction behave as if they have a charge which is a fraction of an electron. And that's mind-boggling, because all these systems are composed of individual electrons. So you would expect that whatever you observe as the effective charge moving through the system would be a multiple of the electric charge. However, because of the correlated coherent motion that you induce under these conditions, the electrons manage to behave in a way that the effective particles, which is a composition of many electrons, have a fraction of the electron charge. Again, when this was discovered, it brought a revolution, and several Nobel Prizes were awarded for the discovery of the quantized currents in these situations. They're called Hall currents, the quantized Hall effect, and the fractional quantized Hall effect. So it really is a very interesting system to study. The physics is very rich and very unexpected in many ways, and understanding it, this physics is a big challenge. So these fractionally quantized effective particles have driven the imagination of physicists to produce elaborate theories that capture this, how exactly it happens. Moreover, in graphene, in the superconducting graphene that we were discussing a moment ago, there are signs that similar effects take place. So under certain conditions, if you adjust the number of electrons in the system and so on just right, you get these effective particles, which are combinations of many electrons, that have a charge which is a fraction of an actual electron charge. Typically 1/3, 2/3, 4/3, things like that.
That's amazing.
really,
So when
really
that
bizarre.
happens, just off my mind being blown
Yes.
off, fermions acting as bosons before, do they still behave as fermions, or do they behave more like bosons? Or
Yes. Well, this is even more interesting, because fermions and bosons are characterized by the following basic property. If two fermions exchange positions, then the system behaves as if you changed its properties by a factor of -1. So imagine that if you have a mirror and you have the image of something on this mirror, it's sort of flipped, right? So that would be the flipped image. I'm trying to capture in words this property of the electrons exchanging place, two fermions exchanging place, and acquiring an overall factor of -1.
So what's actually flipping about the system? Is it one of the quantum numbers?
Yes,
or is it,
basically
right.
yes. The wave function, which is the way that we describe quantum mechanical systems, acquires a phase equivalent to changing its sign, a -1.
Okay.
So that's for fermions.
Okay.
For bosons, if you exchange two of them, the phase doesn't change. It's the same. So you can think of this acquiring an overall factor of +1. It's exactly the same, multiplying by
completely symmetrical.
completely symmetric, exactly.
Okay.
Now these particles that have fractional charge of an electron can acquire a phase somewhere between those two.
Right.
So that's even more bizarre. So because the phase can be anything, they have been called anyons. They're not fermions. They're not bosons. So they're called anyons, and there's a lot of very interesting physics associated with this.
That's amazing.
Yeah, it is. Yeah. So that's one of the things that in the beginning you asked me, what do I find very interesting and fascinating? Why do I find solids? It's because in solids you have basically this almost infinite number of possibilities. There's the different structures that we talked about in terms of crystals, different compositions in terms of different elements, the atoms that make up a crystal, and then the electrons, which basically determine all the properties of a solid, have essentially a huge number of possible ways of behaving. It's fascinating. I mean, it's never ending, and it keeps getting more and more interesting, more and more complicated as we probe the details of the atomic structure, and we come up with more interesting arrangements of the atoms and so on.
So what have you been able to do with these arrangements so far? What are the amazing things that you've been able to accomplish, and what do you think what are you aiming to accomplish? What's the goal? What do you think lies in the future of this field?
A lot of the devices that we use in everyday applications are dependent very sensitively on the properties of the solids that I was just describing. So, for example, all the chips that run the computers are dependent on how exactly electrons can jump from one state to another state, and that's what determines if current goes through or does not go through. So that's the 0 and 1 of a standard bit in a computer. And the levels between which electrons can jump are determined by the properties of the solids. And the interaction with light, how light can get absorbed, and how the system is transparent or not, or how light can be guided through the solid, it all again depends on the properties of the electrons. And all the communication devices that we have exchange signals based on these properties. They can absorb electromagnetic signals or emit electromagnetic signals depending on the exact properties of the electronic states. So everything that we do in terms of electronic devices is very much dependent on these properties. And there's all sorts of exotic devices that one can think of that may lie in the not so distant future that again take advantage of these properties. For example, we talk a lot these days about quantum computers. So quantum computers are based on the properties of atoms and molecules and solids at this level. So, for example, there's some type of quantum computer based on superconducting rings. So you can imagine that you have little superconductors, and the way that currents flow in these little superconducting rings can act as the basic elements for a quantum computer. So having this possibility of different types of superconductors, different shapes or different ways that we can make these superconducting rings is extremely useful for possible implementation of the quantum computing idea, or realizing the quantum computers that people are trying to.
So to do that is the challenge then trying to increase the temperature that superconductors can operate at, so they can work within these computers? Or?
Exactly. That's one aspect of it, because as we were mentioning earlier, all these interesting phenomena take place at a very low temperature. So one of the goals is to make it feasible for this to happen at slightly higher temperatures, as high as we can go. They're still low, relatively speaking. They're way below the freezing point of water, for example, and certainly some much lower than that, but still quite a bit higher than the absolute zero that we mentioned. So if we could do that, that would be really wonderful. Moreover, even though solids are essentially crystals, as I was describing earlier, there are also imperfections in these crystals called defects. And it is these defects that can also introduce very important, very interesting properties to the behavior of the solid. And these defects can act as the centers where by light you can control the behavior of these microscopic objects, and those would be then the qubits, the quantum bits that would form the basis for a quantum computer. So not only you want to understand the properties of an ideal crystal, but also defects that you can introduce to this crystal. Again, if you can control exactly how the defects are placed, where they are placed, what atoms they substitute
so it's
in
not
the
like a
regular
natural
crystal.
sort of defect, it's like a very intentional.
Exactly,
Sort of
it's very intentional and
understanding
control.
how.
Exactly.
Okay.
Exactly.
Interesting. That's amazing.
So
That's a route that can go down to, yeah.
Yes.
Particularly
Yeah.
as, since I'm sure, given the nature of the research, quantum computers will help in itself to advance the research further.
Absolutely. That's one of the ideas, that quantum computers will be much more efficient in simulating quantum systems,
Yes.
and therefore give us a deeper understanding and a better knowledge of what exactly quantum phenomena mean. Like we were discussing earlier, how do all the electrons all of a sudden decide to be in this very coherent state, the superconducting state? What makes them do that exactly? It's not a trivial thing to understand.
Would that be the first thing you would try if you had a quantum computer right now in this room? What would be your first sort of
maybe
operation?
That's possible. It's certainly a very interesting scientific question, but there
Yes.
are also many other important practical questions that could be addressed with a quantum computer. For example, we could study better how molecules interact with other molecules, like a tiny molecule interacting with a much bigger one. A tiny molecule would be a drug, the much bigger one would be a protein. How a drug affects the function of a protein, and what exactly does it do, so we can design drugs that have very specific effects and hopefully have a big impact on society and health and so on, cure cancer or something like that. And that's at some level that's also a quantum mechanical phenomenon, the interaction of small molecules with larger ones. It's also a problem which by its nature is very complex. So it's not easy to figure out all the possibilities, explore a lot of options, and then settle down on the few that would really solve a medical problem. So that's something that could be addressed with quantum computers, because they are so much more efficient in searching lots of possibilities, in simulating quantum mechanical types of situations, and sorting out what can happen, and make the right choices for these combinations of molecules that can address a medical problem.
Is the development of sort of machine learning systems something that's also useful in work if you're going through all these different options?
Yes, absolutely. Yes, machine learning and artificial intelligence methods are very important, and they're employed more and more frequently these days in the research in these topics, as well as many other topics. And one of the issues that they may help us address is, we're talking about materials and solids and so on. So there are lots of materials in nature and lots of types of solids, but with the atoms in the periodic table, there are many more possibilities for making artificial materials. So those are materials that are not necessarily the most stable ones, but stable enough to be useful for particular applications. but we can't conceive and explore all the possibilities for combining all the different elements to see what types of materials we could synthesize. And it's very difficult to try that in the lab because it's very time consuming, very expensive, and so on. But with artificial intelligence and machine learning methods, we can, having learned a few rules of how things can be synthesized, can be put together, we can explore many more possibilities, sort out what's interesting, and focus on that and suggest it for experimental realization. So this is used quite a bit these days, namely searches for new materials, exploration of possibilities for creating new materials, artificial materials, by combining different types of atoms in different types of structures. And it's actually been quite successful. Some magnetic materials, it's hard to find good magnets, especially in two-dimensional magnets and so on. This is not a trivial undertaking. And there have been predictions based on the use of machine learning methods, and they have been verified of how to create new types of two-dimensional magnetic materials or materials that have other special properties.
Yeah, that's amazing.
So it's very exciting. So
yeah,
it's not easy to do, but it's very promising and very exciting.
Okay. So I'm taking it then you said you need to figure out the rules to be able to use these sorts of algorithms. So is that the word, is that why graphene is used, for example? You're at the point of figuring out the rules.
Yes.
And
yes. So yeah, that's one way. So to study materials that we already know to greater depth and understanding what governs their properties. Another set of rules, so to speak, is empirical rules that come from feeding the algorithms all that we know about what matters in determining the properties of a material. And then letting the algorithm apply this information learned through a very large data set to other possible combinations. So it's like showing a lot of images of things that you know, like birds and animals and so on, and then the algorithm recognizes other patterns, other similar types of images. So that's one way of doing it. Finally, there's a slightly different way, which is to try to train the algorithm in understanding the basic rules of quantum mechanics. So we know the equations of quantum mechanics. They're hard to solve, as we were discussing earlier, but we can train algorithms to figure out how these rules might apply in different situations, and therefore be able to guide us to predict new structures by having been shown the essential physics. So that's one type of approach referred to as physics-informed machine learning. So we supply some of the basic rules that we know, then we create algorithms that obey these rules and try to solve problems based on this knowledge.
That's amazing.
It is, yeah. So
I know a lot of people are worried about AI taking their jobs and stuff. Should physicists be worried if these algorithms are able to start to grapple with these sorts of concepts?
I don't feel like that. I think it should be viewed as a really interesting tool that can elevate the way we think about problems to a higher level. So we don't need to worry about lots of details and lots of tedious types of patterns, right?
Yeah.
But then we can pose more interesting questions and guide the scientific research at a higher level. So I think there's a lot of interesting possibilities there.
Okay. So for young people coming into this who might want to address these questions, what are the chief questions within this field that they should try to go about addressing? I know you mentioned that increasing the temperature of superconductivity was one. Are there any other sort of big problem areas or things that are being actively worked on?
Yes. Well, another really important aspect is the strength of materials. What makes a material strong, which in some contexts means very ductile. You can try to deform it and it doesn't break.
Right.
That's one way of defining its strength. Or the opposite. If you have a material, how can you make it more brittle? How can you make it easier to break apart? Because you can imagine that there's a lot of issues related to the strength of materials. So that's a very complicated process having to do with interactions which start at the atomic level again. So somehow atoms start falling apart, bonds start breaking here and there, and all of a sudden then the material starts breaking apart at a large scale. How does that happen? That's a very complicated process at the atomic level. And it would be important to have a grasp of this, have a handle of this, again starting from the atomic level, starting from the composition and the structure of the solid at the atomic level, and then being able to predict at a much larger macroscopic level the behavior under external loads, under conditions of chemical reactivity, corrosion, and things like that. So that's very important for many, many practical applications, as you can imagine.
Yes.
And it's a very complex problem. So, of a different nature than we were talking about earlier, but still,
supercomputers,
right? But still, ultimately, again, related
yes.
to the atomic level structure and chemical composition of a solid.
Right. I guess everything we use in everyday life relates to that.
Yes, absolutely. Absolutely. Like people, for example, are talking about the hydrogen economy and using hydrogen as the fuel for cars and so on. Well, hydrogen is an element. The hydrogen atom is the smallest atom in the periodic table, and it's really quite fascinating because it's the hydrogen atom is a proton in the nucleus and an electron around it. There's no simpler system than that, right? So all the nuclei of all the other atoms, elements are more complicated than just a proton. And all of them, all the other atoms, have more electrons around the nucleus than just one electron of the hydrogen atom. So that's the simplest possible system that you can imagine. Now, when you put hydrogen in a solid, it basically loses its electron. The electron goes and sort of becomes part of all the other electrons in the solid. So essentially you have what you have left is a proton moving around the solid. So that's a very tiny object, can move around very easily in the solid. So it's very hard to store hydrogen in a solid or contain it in the solid because it can easily diffuse around, and that's a source of problems. There's a phenomenon called hydrogen embrittlement. Because it can diffuse around, because it's so small, it can induce this kind of brittle behavior in other solids. So it's hard to contain hydrogen. It's not a trivial thing to create hydrogen containers.
It's a problem if we want to use it.
That's right. So exactly. So we better understand exactly how to do this,
right?
So that the containers don't start falling apart after a small amount of use.
Yeah, and I imagine along those sorts of lines, this research might also be relevant to battery technologies.
Absolutely.
On the line of powering other things.
Yes, exactly. Absolutely right. A few years ago, I was involved in research of this type.
Okay.
We were trying to figure out how to create materials that could store much more energy per unit volume than the standard battery materials that we use for batteries these days. And that's not easy because we can indeed create materials where you can use, you can store much more energy, but of course you're going to be able to also get that energy out. That's the battery, right? You draw current from the battery, so you draw energy from it, and then you have to recharge it. You put the charge back. So in this process of charging and recharging, basically you're taking atoms or ions outside of a material, and then when you charge it, you put it back, and so on. So if you create a material that can store a lot of energy, then this process of charging and recharging changes its volume very drastically.
Right.
So after a few cycles, the material sort of falls apart.
Yes, I imagine there's a lot of heat associated with that as
There's,
well.
there's
and
heat
exchange
associated
of
with
amount
that.
of energy, yeah.
Exactly, absolutely. So it's not a trivial a problem to create a material which can then survive many, many cycles of charging and discharging. Okay, you can do it once or twice. So you have high energy density, but it's useless.
Yeah, we want to change the battery in our cars every drive. Yeah,
that's right. Right. So these are very interesting problems with very important implications for for technology, and they still need to be analyzed at this very fundamental level. So we need to understand exactly what is happening when you charge the battery. How do atoms get inserted? The ions get inserted in the material. When you discharge it, how do the atoms come out? And how this process can be controlled so it can be repeated many, many, many times.
Okay. So how did you go about trying to solve that problem?
Well, people are still working on this. It has not been solved, but we did again a lot of simulations trying different types of crystals and introducing different types of ions into these crystals, like lithium ions. That's the standard type of ion that is used in batteries, and figuring out how exactly lithium atoms can move in and out of a material, and what should be the optimal structure to facilitate this and to make it a process that can be repeated. We had some ideas. Some things were tried experimentally, some were successful, others not quite so successful, but it's a very active area of research, and the batteries themselves are quite complicated. There's the electrolyte, the membrane that separates the electrolyte from the anode and the cathode, and so on. So it's not just one material. Many different types of materials have to come together to produce the design.
In complicated ways.
Exactly,
yeah.
exactly.
Okay.
Like we were talking about earlier, graphene could be the ultimate membrane that can separate one material from another.
Right. Yes.
So that has been tried to some extent. There's probably much more room for improvement there, and so on.
That's fascinating. I mean, graphene seems to, in particular, have a vast amount of potential.
Exactly.
Just as a final question, because I think we might be running out of time.
Okay.
What advice would you have for people such as myself who might be considering a future in research, and in particular a future in researching materials?
Yes. In my experience, what's really important is to be very solid on the fundamentals, like math and physics, to really absorb the very important mathematical concepts and physical concepts that will help you think in a critical way. And on this basis, I think you can do a lot of wonderful things once you feel confident about how nature works and how you express the workings of nature in terms of mathematical equations that capture this behavior. But without this, you're not on very firm ground. These days we can compute a lot of things. Now we can translate the math that we use to write equations that describe nature. We can translate that into computer code, run a lot of simulations, and get a deeper understanding. But if we don't understand the fundamentals of what we're doing, the results may not be very reliable or relevant. So that's my concern, my most important concern for young people. And I think
understanding the basics.
Yes, and I think this kind of familiarity and grasp of the fundamentals is fading a little bit. Students don't give as much attention to this as they should, which I think is a mistake. Anyway, so I think that's very important. So, just to give you an example, in the last few years, I've been teaching here at Harvard a course which is called Introduction to Computing for Scientists and Engineers. So basically we train students, we teach students how to use computer languages and computer code to model different types of systems. But it really is a combination of math and coding. So we take the equations, the math that describe different types of systems, and figure out how to translate that into code, giving equal weight, equal importance on the two aspects. Because if you just learn how to write code, but without having this deeper understanding of what you need to code, then it's not going to get you very far, at least in the fields of science, materials, and so on.
Okay, and is, I mean, talking about different materials, is the study of chemistry at all important? Is that useful, or
absolutely.
is it not?
Absolutely,
Okay.
absolutely. Right. Physicists don't usually pay that much attention to chemistry. Yes. I'm an exception. I think chemistry is really important.
Yeah.
And understanding the way that chemists think about how different atoms are linked together, what is the chemical bond and so on, is very important for the types of problems that we were discussing earlier, for really getting insight into how materials behave, what makes them stable, what makes them unstable, how they fall apart. All these are essentially traced to chemical reactions, chemical bonding, chemical reactivity, and so on. So it's a very important aspect of this.
You'd recommend that people going into this take a chemistry module at some point?
Yes, I think this is actually very helpful, very important.
Okay. Well, thank you so much for your time. That was truly fascinating.
It's a pleasure.
I appreciate it.
Okay.
Thank you for tuning in and for your continued support. I hope you found that discussion as fascinating as I did. There were certainly quite a few things we spoke about which blew my mind. More discussions which I recorded in the US are soon to come, so please like and subscribe and stay tuned for more.